Hey everyone, in today's lesson we're going to be talking about some applications and examples of using the Sylow theorems. In the past two videos I proved to you the first, second, and third Sylow theorems, and so this video will be dedicated to using those theorems to prove different examples to help you get some practice. Okay, so before we get into the examples, let's just do a quick overview of what the Sylow theorems gave us. So the Sylow theorems told us to start with a general group G, and they first let us, using the first theorem, so I should write Sylow 1. So Sylow 1 let us take a general group G and then basically find the existence of P Sylow subgroups. P Sylow subgroups. This is what Sylow 1 did. So now that we know that these exist, we can use Sylow 2 and Sylow 3, Sylow 2 and 3, to then try to find normal subgroups. The reason why this is helpful is because, well, in general, if you have a group G, there's not a ton of different ways. I mean, we've discussed a couple of finding subgroups in G, in just a general group. Some of them that we've discussed are maybe the center of G, which is all those elements which commute with all other elements. The Sylow theorems give us another way, which is the existence of these P Sylow subgroups. So now we can prove the existence of many different kinds of subgroups. A natural question that we will find is very fruitful is, when are some of these subgroups normal? And we will discuss in later lessons, we will discuss how finding normal subgroups is often very important to determining the structure of the entire group. Finding normal subgroups is important for the structure of G. But for now, just accept that this is something that's worth studying. So let's just do a quick reminder of the Sylow theorems that are going to help us. And I recommend, before attempting any examples, to just write these facts down and try to use them as you see fit. Okay, so the first one says if p to the n divides the order of G, but p to the n plus 1 doesn't divide the order of G. This is just saying p to the n is the highest power of the prime dividing the order. Then there exists a subgroup H in G where order of H equals p to the n. Basically saying there's a P Sylow subgroup. Okay. Then the second fact that will be helpful to us is that the number of P Sylow subgroups, as we proved last time, is equivalent to 1 mod P. And we also proved that NP must divide the order of G divided by P to the n. Where this is, you can think of this as the order of any P Sylow subgroup in G. These two facts together will be very helpful for whittling down what NP can be, and the third fact tells us why determining NP is helpful. We get that if H is a P Sylow subgroup, then H is normal in G if and only if NP equals 1. Okay. So we proved last time all of these different facts, so if you are unsure about them, reference those videos. But if you accept them, you should hopefully remember that or see that if we can determine what NP is, if we can determine it's 1, then we found a normal subgroup. So that's the main goal, is trying to determine that NP is 1 for at least some prime, because then we can find a normal subgroup. So let's just introduce a quick definition that will help us, and is a common definition when talking about normal subgroups. A group G is simple if it has no normal subgroups. Has no normal subgroups. Okay. And the reason why this might be helpful is because we can now try to use the Sylow theorems to prove that groups are not simple. And it happens to be that it's often valuable to be able to prove a group isn't or is simple. So that's what we'll attempt to do with many of our examples. Okay, let's start with example 1. I recommend before trying all of these that you try it yourself and then look back on what I did. Because it's really not helpful to look at my proof unless you've tried it yourself. I mean, it will help you see through the process, but just for your own learning, it'll be more valuable if you try it yourself first. So let's assume that the order of our group is 12. Okay. Now we're going to prove that G is not simple. Okay, let's prove this. Okay, we get that 12 has a prime factorization of 2 squared times 3. So we have the primes we can choose are either p equals 2 or p equals 3. 2 or 3. Let's look at what happens for both of them. So I get that n2, which is the number of 2 Sylow subgroups, is 1 mod 2. And I get that n3, which is the number of 3 Sylow subgroups, is 1 mod 3. And I also get that n2 has to divide 12 over 2 squared. And I get that n3 has to divide 12 over 3. This just comes from the facts I stated at the beginning. You know it has to divide the order of the group divided by the order of the p Sylow subgroup. In our case, we can go up to 2 squared for 2 and just for 3 for 3. So if n2 has to divide, in particular this means n2 divides 3 and n3 divides 4. So I get that n2 has to be in 1 or 3, it's either one of these, and n3 can be 1, 2, or 4. These are just all the divisors or factors of 3 and 4. But now we can use our other facts that n2 is 1 mod 2 and n3 is 1 mod 3. Well, I see that 1 is 1 mod 2 and 3 is 1 mod 2. So all of these are plausible. If I look at n3 though, I get that 1 is 1 mod 3, 4 is 1 mod 3, but 2 isn't. So I can immediately eliminate 2 as a possibility, and now I know n3 has to be either 1 or 4. Okay. So what we determined so far is that n2 equals 1 or 3, and n3 equals 1 or 4. So if n2 is 1, then G is not simple. Since we just proved, we know that if np is 1, then the p Sylow subgroup is normal, is not simple. So for the sake of argument, let's assume that n2 is 3. Similarly, we see that if like n3 equals 1, then G is not simple. So, for the sake of argument, let's assume n3 is 4. Now we're going to use a proof by contradiction, which is assuming n2 is 3 and n3 is 4, to find some contradiction in the statement to show that either n2 or n3 had to be 1. Okay. So if n2 is 3 and n3 is 4, well then I can list the p or the 2 Sylow and the 3 Sylow subgroups. Let's call them p1, p2, and p3, which are the 2 Sylow subgroups, S2 of G. And then let's call them q1 through q4, which are the 3 Sylow subgroups. I get that the order of each pi is 4, 2 squared, and the order of each qi is 3. Okay. So what you should notice is that, well, qi, since it has order 3, has to be cyclic. It's prime order, it has to be cyclic. So I can write it as 1, g squared. But you should notice that these two elements, g and g squared, both have order 3. So in each qi, I have two elements of order 3. I also know that qi cannot equal qj, where I doesn't equal j, because I'm choosing 4 distinct q's, or 3 Sylow subgroups. In fact, I know that their intersection has to just be the identity. You can think through this yourself. If I have qj, which maybe equals 1, h squared, you can pretty clearly see that if there's any intersection, for example, if h was g or h was g squared, we would have a problem they would be equal to each other. So this can't be the case. Another way of proving this is knowing that qi, the intersection of qi and qj, is a subgroup of qi and qj. And because of this, it has to either be just the identity or the entire group. Can't be the entire group because they're not equal. So it has to be the identity. And that's because 3 is prime. Okay. So in total, I find that each qi has 2 elements of order 3. Elements of order 3. So in total, I get 2 times 4 equals 8 elements of order 3. Number of elements of order 3 equals 2 times 4 equals 8. Okay. Now let me see if I can find the elements of 2 and 4 by looking at the 2 Sylow subgroups. If I can somehow prove that there's too many of them or it exceeds the size of the group, I can find a contradiction. So we see that P1 has 4 elements. Okay. And I get that P1 and P2 are distinct. So P1 and P2 together have to have at least 5 different elements. Have to have at least 5 distinct elements. 5 distinct elements. Okay. But if that's the case, well, I know all those elements are of either 1, 2, or 4, because they have to divide the order of the group by Lagrange's theorem. So using what we proved above, I can say the number of elements of order 1, 2, 3, or 4 has to be greater than or equal to the 8 we got from elements of order 3 plus the 5 we just proved for 1, 2, or 4, but this equals 13, which is greater than 12, which is the order of the group. So this must be a contradiction, because if all of these elements have to be in the group, then they have to have total size less than 12, because the group is size 12. But if we prove that they're over 13, then we found a contradiction. Thus, we see that either n2 or n3 must be 1. So G is not simple. Great. So you'll see that this argument of kind of proving by contradiction, by saying assume that none of them are 1, and then finding some contradiction in the total size of elements, is a great way of utilizing the Sylow theorems. Okay. So now let's move on to example 2. So let's say the order of G equals 30. Let's prove that G is not simple. Okay. Proof. So we're going to factor 30 as 2 times 3 times 5. So we get that we can either choose p equals 2 or 3 or 5. Let's look at each of those examples. So if I look at, let's say, n2, I get that n2 must be 1 mod 2. And since n2 must divide 15, because 30 divided by 2 is 15, I get that n2 must either be 1, 3, 5, or 15. Okay, n3 is going to be 1 mod 3. And n3 is going to have to divide 2 times 5, which is 10. Using these together, I get that n3 has to be either 1 or 10. Okay. Finally, if I have n5, which is equivalent to 1 mod 5, I get that n5 has to divide 2 times 3, which is 6. Because of this, I get that n5 is either 1 or 6. Okay. Now, I'm just going to use n3 and n5 here. That happens to actually be enough. But first, we're going to assume by way of contradiction that n2 is not 1, so it's either 3, 5, or 15. We're going to assume that n3 equals 10 and n5 equals 6. And we're going to see what happens. So we get that each 3 Sylow subgroup, which is going to have order 3, is going to have 2 elements of order 3. So we get 2 times n3 equals 20 elements of order 3. And then we also get that there's 5 Sylow subgroups, each with a similar form of argument, has 4 elements of order 5. You can check this for yourself. So we get 4 times n5 equals 24 elements of order 5. Using this together, we find that the number of elements of order 3 or 5 equals 20 plus 24 is going to equal 44. But 44 is a lot greater than 30, which is the size of our group. This means that this leads to a contradiction. Thus, either n2, n3, or n5 is 1. In particular, since we didn't use N2 could have been 1 this entire time. This actually proves that, in particular, N3 or N5 is 1, which is a similar statement, but, that's just the way the argument goes. So this proves that G is not simple. In this case, we didn't end up needing to use N2 because N3 and N5 were so large that they immediately caused the contradiction. If it happens to be that we find the number of elements of order 3 or 5 is just under maybe 30, let's say, then you could have used N2 and then found a contradiction there. Luckily, we don't need to in this case. So, through both of these examples, you might ask, when are groups simple? Groups simple. Because both of the examples we've done have shown that they're not simple, and maybe most of the groups you can think of have some normal subgroup inside of them. Well, this is a great question because it happens to be that simple subgroups don't appear for a while. To be that, the first simple subgroup is of order 60. So you have to get up to 60 elements to first possibly find a simple subgroup, and even then, not all subgroups of order 60 are necessarily simple. We get that I haven't introduced this, but it's called the alternating group, A5, which is a subgroup of S5, the symmetric group on 1 through 5, is simple. This is a very cool realization, and it's kind of helpful for many of the proofs now. If you could say that, if G is less than order 60, then it has to not be simple. But that probably won't fly if you're supposed to use the Sylow Theorems. Since all of these groups from 1 to 59 are provably not simple no matter what group they are, maybe we should try generalizing. So let's try generalizing. To groups of a more general order and see if we can still find that they're not simple. To find even more non-simple groups. Non-simple groups. Okay. So this will be our example 3. So let the order of G equal P times Q, where P and Q are primes, and P is less than Q. These are primes. Okay. Then I want you to prove that G is not simple. Proof. So we're going to find that NP is going to be 1 mod P. So there's 1 mod P Sylow subgroups. And I get that NP has to divide Q, because PQ divided by P is Q. And NQ is 1 mod Q. So there's 1 mod Q Sylow subgroups. And NQ has to divide P. Okay. Well, because PQ divided by Q is P. Well, we see, I can actually just look at this example here. If NQ is 1 mod Q, and NQ has to be either 1 or P, well, let's say that NQ was P. Then we would get that P is equivalent to 1 mod Q. But remember that we assumed that P was less than Q. So this can only be the case if P equals 1, but 1 is not prime. Thus, we get that this leads to a contradiction, so NQ has to be 1. Great. So we instantly prove that the Q Sylow subgroup is always normal, which is great. Thus, G is not simple. You might have thought that was like a little too easy, so let's make it a little bit harder and ask, when is the P Sylow subgroup also normal? Also normal. Okay, well, let's see. We get that NP is equivalent to 1 mod P, and NP has to be either 1 or Q, because remember that P and Q are both prime. So if NP, let's assume by way of contradiction that it's not normal, so NP has to equal Q. I get that Q is equivalent to 1 mod P. Or Q minus 1 is equivalent to 0 mod P, which means that P is a factor of Q minus 1. So P must divide Q minus 1. Thus we find that if P divides Q minus 1, then the P Sylow subgroup is not necessarily normal. Not necessarily normal. We get that this might not necessarily be normal because this basically tells us that Q is 1 mod P, since Q minus 1 is divisible by P. So Q minus 1 plus 1, which is Q, is 1 mod P. So it's a possibility, but it also tells us that if P doesn't divide Q minus 1, then NP has to equal 1, because otherwise it would contradict the fact that NP is 1 mod P. So the P Sylow subgroup is normal. So we see in the general case, we can make these interesting claims where we have criteria such as P dividing Q minus 1, which tells us even more about the normal subgroups in G, where G equals P times Q. So now that you've gotten some practice, let's give you some examples to work on. So some homework examples. The first one is going to be prove that if the order of G equals 105, then G is not simple. In general, try to prove if the order of G equals P times Q times R, where P is less than Q and is less than R, and they're all prime, then G is not simple. Okay. Second example is prove if the order of G equals P times Q to the N, where P is less than Q and N is some positive integer, then G is not simple. finally, this third one, which is going to be a little difficult, so harder, is prove if the order of G equals P squared times Q, where P is less than Q, and remember they're still all primes, then G is not simple. And I should give credit, both of these examples here are credited to Sam Raskin, Professor Raskin, as helpful examples for group theory and using the Sylow theorems. It actually happens to be that there's a theorem called Burnside's theorem, which you're not allowed to prove these examples, but Burnside's theorem basically tells us that the order of G is P to the n times Q to the m, where P is less than Q and they're prime. Then G is not simple. Not simple. Which is very interesting. So basically it kind of generalizes all of these examples together into one. And this is actually a pretty deep theorem. It's not easy to prove at all. Quite challenging. Okay, hopefully this was good practice for using the Sylow theorems, and you can use these examples to get even more practice. Thanks for watching.